Hello and welcome. You guys have all been waiting for this awesome Monday because it is Maths Mondays on Learn Extra Live. How are you, Dina?
Good, thanks.
Good. We're doing maths today and we're doing trigonometry. Hey, Dina.
Yeah, grade 10s, we have done the session before, but we're looking at trigonometry again, the theory behind triangles and how the sides and the angles are related. So we're going to have another session on that. So join us in a little while.
Awesome. Revision is always good, as you guys know, and trigonometry is one of the best topics in maths. Tina, you can walk over to your board.
Thanks.
So you guys know, of course, that it is Monday, and we have some prizes. We have the Casio calculator, and we have the labeler. Make sure that on Facebook and on Twitter, you are the number one mindsetter today, so you can win prizes. Remember, every Monday, there's always prizes, and every Monday, I'm waiting to see that really special mindsetter. Of course, thank you to Liberty. Liberty is absolutely awesome, and our Facebook page, just for a reminder, is facebook.com/learnextra, and our Twitter handle is @learnextra. Guys, I'm looking forward to this lesson, so just make sure that you have joined us, and in case you're not here yet from school, or you're just getting in, make sure that you hurry up and tune in so fast, because we are ready for such an awesome trick show. Hey, grade 10s, I know you are. Dina, are you ready for us?
I'm ready. Thanks,
Awesome.
Katlehu. Right, time to get going on the trigonometry. And what we're going to do is three things. In the first section, we're going to just have a look at how to find the side and the angle of a triangle. In the second part, we're going to look at some trig equations. And in the last part, we're going to look at the Cartesian plane, which some of you may or may not have covered in class. So those who have, it will be good revision. For those who haven't, then you'll have it for the first time. So let's get going. The trig ratios, as we know, are defined by sine theta, cos theta, and tan theta. And without a triangle, we are unable to define the ratios. So over here on the side, I've got a diagram that depicts the side that is adjacent to the angle. And some of you may be saying, but this side is also adjacent to the angle. Well, that side is opposite the right angle, so it's always got a special name. So that side will be the hypotenuse. And that side is fixed. It doesn't change depending on where the angle is. So my hypotenuse is always the side that's opposite the 90 degrees. But now this white length here is opposite this angle. And we've now got that it will be referred to as the side opposite the angle, whereas the orange side will be referred to as the side adjacent to the angle. Now, if we were looking at angle A, for example, this white side would be the adjacent side to the white angle, whereas this side over here would be opposite to angle A. So let's look at the definitions. For sine, we need the side opposite, which is C, and we need it divided by the hypotenuse. So we've got the fraction C over B. Cos theta is the adjacent side over the hypotenuse, so that would be that fraction there. And tan theta is the opposite side, which is C over the adjacent, so C over A would define tan theta. So for those of you who have already done your own memorizing, there could be this code word, SOHCAHTOA, to help us remember how the sides are related to that angle. So that would be opposite of our hypotenuse, cos adjacent of our hypotenuse, tan opposite of our adjacent, so that this is referring only to the first letters of the ratio and then the fraction portion, C fraction portion, T fraction portion. Right, but this year there's also the reciprocal ratios that we need to look at. And the reciprocal ratios are cosec is equal to 1 over sine. So in any relationship, you would have it as the hypotenuse over the opposite. Then we would get sec, which is a reciprocal of cos, and there we would get the hypotenuse over adjacent. And then finally, the cot ratio is a reciprocal of tan, and that would be your adjacent over your opposite. So those are our reciprocal ratios. And if you take the product of sine and cosec, you'll obviously get 1, because since it's So we could write it over here that if I take cosec and I multiply it by sine, I will get 1. So it's just rearranging this equation to multiply across by sine theta is equal to 1. Right, in terms of calculations, what does cos 48 degrees give us? And for that, your calculator works quite well in just from left to right. So cos 48, you would just fill in your angle and you would ask it for the ratio. And it's 0,669, usually 3 decimal places or sometimes 2. In this case, if we left it to 2, then it would be 0,67, correct to 2 decimal places. Then 2 sine 35, we would have a coefficient of 2, so we're doubling whatever sine 35 is. So double what sine of 35 degrees is, and that gives us 1,15. 1,15. Tan squared 81 is quite an interesting one because tan squared 81 does not mean that you square the angle, it means that you square the ratio tan 81. So if we have to rewrite this, we would say it's the same thing as tan 81 all squared. Okay? And the same thing would apply for 3 sine squared 72. But let's have a look at what that gives us. So we would get the tan of 81, and then we'd like to square it, and we would get 39,8. Now I just want to try something. If we have the tan of 81 and we square it, what do we get? 39,8. So as you saw earlier, the square was only around that 81, and it also gave us 39,8. So the calculator doesn't mind if you leave out those introductory brackets. So it facilitates the calculation there. So that gives us 39,86. 39,86. Right, and then 3 sine squared 72, what would that give you? 3 times sine of 72, and then we want to square it. What does it give us? 2,71. 2,71. Okay, so the only problem with the calculator is that you're seeing the calculator do this. You're seeing 3 times sine, and then the calculator does a 72 and does a squared. And it looks like the angle's being squared. So it's quite problematic on the calculator, the way it's showing it up. But you've actually got to understand that the calculator's not squaring that angle, but it's actually squaring the ratio. So if that confuses you, then you could just do that and put the square out there. Then at least you know that the ratio is actually being squared. Okay. Right, so that's just briefly how the calculator calculates the various ratios. Let's now go on to some questions related to, in each of these triangles, we are going to find the length of the side or the magnitude of the angle that is marked with a letter. So before we begin, I'm just going to, up here, put our acronym for reminding ourselves how the ratios actually work. Okay, so in this triangle, first focal point is to focus on the angle and to say, if that is my position of the angle, then how is this A related and how is this 62 related? Well, the 62 is definitely the hypotenuse, and the A is definitely the side that's opposite that. So in our scheme of things, we would have the opposite side, something about the opposite side, and we've got something about the hypotenuse. So therefore, that's the ratio that we are using. So you can always write that acronym to decide what has been given and how you're going to utilize the ratio. So we would start with the sine of 37. The sine of 37 is equal to the opposite over the hypotenuse, which is 62. And now we need to solve for that equation. So we've got A is equal to 62 sine 37. Once we're at this stage, we can now use the calculator. 62 multiplied by sine 37, and that gives us 37,31. So A is 37,31, whatever units they are giving us, in which case it doesn't have a unit at this stage, but this length here is 37,31. Okay, then if we look at the next one, and again, if we write up our acronym, just to establish what has been given to us. So we are given an angle, and we want to find the side that's opposite, and we've been given 21, which is the side that's adjacent. So if we go to the information, we want to find the opposite, and we have the adjacent. So that's my ratio that connects or links the opposite and the adjacent. So there's my angle there. So we will start by saying that the tan of the angle given is equal to my opposite over my adjacent. Again, I want to solve for B, so I want to multiply this side by 21. Look where I'm putting it. It's 21 times the tan of 23, because this gives me the ratio, and then I need to multiply by 21. It's not tan of 23 times 21, so I'm not taking the angle and multiplying that by 21. So now I can go to the calculator and say 21 times the tan of 23 degrees, and that gives me 8,91. So B forgotten what it is. 8,91. 8,91, again, whatever units you've been given. Okay, next one. Right, we've got, let's see, this one hasn't been given a side, so let's make that C there. Okay, so let's again write down the acronym, so SOHCAHTOA, and which of these ratios will relate. So we've got the hypotenuse, so it could be sine or cos, and we've got what's this side in relation to the 55 degrees. It's next to it, so therefore it's adjacent. So we have to find the adjacent side, we have the hypotenuse, so we have cos there. We can say therefore that the cos of the angle is equal to the fraction C over 19. So C will equal, solve for C means we need to multiply by 19, so it's 19 cos 55. (19 times cos of 55). Okay. Right, we can go into the calculator. 19 times the cos of 55, and we get 10,90. 10,90. Right, this one, let's write down our acronym, and let's go back there. So let's write SOHCAHTOA. And what have we got this time? We've got an angle, 49. And what is D in relation to 49? And what is 33 in relation to 49? 33 is the side that's opposite the angle. And no, 33 is the side opposite the right angle. So 33 is the hypotenuse. So we could have either sine or cos. But the moment we get a second side, it will eliminate one of those. This is the side adjacent to it. So therefore, this is your adjacent. And this is your hypotenuse. So we have the cos. So we will start with cos 49 will equal the adjacent over the hypotenuse. So therefore D is 33 times cos 49. In other words, using the calculator, 33 times cos 49 times the cos of 49 gives us, and notice the calculator doesn't need degrees because I've got my D. You must always look at the top of your screen, that tiny little letter at the top. There are 3 different angle measurements. There are degrees, there are radians, and there are gradients. At school level, we're only going to deal with degrees. But later on, for those going into technical subjects, they will use radians. And for others, engineers, etc., they will use gradients as well. So you need to check your calculator carefully that you're actually in degrees, because otherwise you're going to get completely different answers if you're using one of the other angle modes. So in this case, we get 21,65. 21,65, and that would be my D. Right, let's see what's happening over here. Okay, we've got an alpha. Okay, so for the first time we're looking at an angle. So let's see with our acronym what we have. Okay, so if we're looking for this angle, what is the side in relation to that angle? That side is the adjacent, and that side is the opposite. You agree? So therefore, we would be working with opposite and adjacent. So we actually need that ratio. So we always start with the angle. So tan alpha equals opposite is 4 and adjacent is 9. And now, how does the calculator know how to find the angle? Well, because it's very clever. The calculator has got a button for the ratio of tan, and as a second function, it's got tan to the minus 1. Cos has got cos to the minus 1, and sine has got sine to the minus 1. So these yellow buttons here are the buttons that find the angle for you. Now, you don't need to write down what the button is or what that function looks like. All you need to do is to take your calculator function, so tan to the minus 1, and you need to fill in that we have a fraction 4 divided by 9. And now the calculator will give you automatically what alpha is. So we don't fill in any minus ones. We just use the calculator and write down straight away what that angle is. And what's that angle? Let's see. Would you like to try and guess? 4/9 is just half of that 1. So let's see. What is it? 23,96 degrees. So that's 23, oopsie. 23,96 degrees. Okay. And over to you, Katlego.
Thank you, Dina. So guys, we're going to go for a really quick break just for you guys to sort your stuff out, write down your rules so that when you come back, you are actually on the ball. See you after the break. Welcome back, Mindsetters. If you have just joined us, we are busy with Trigonometry for Grade 10s with Dina. It has been an absolutely amazing show till now. So if, in case you know someone who struggles with trigonometry, or if you know someone who really loves trigonometry, please tell them to join us right now because it is still going to be really awesome. Over to you, Dina.
Thanks, Katlego. Right, everybody, we were working with finding the angle, and I've got one or two more to work with. But I know some of the questions that were posted revolved around the issue of decimal places. Do we always round off to 2 decimal places if we're not told? Well, decimal places are one of those things that have got a very practical value in life. So if you're doing technical subjects, if you're doing measuring, if you're doing architecture or engineering, or any of those subjects that require you to do with real life scenarios, you would really be informed by the context that you were working in, what the decimal places were relevant. So let's say even if you were a doctor and an anesthetist and you were injecting a patient with some kind of liquid, and you said, must I inject 2 decimal places or must I inject to no decimal places? Well, that's saving a life when you're dealing with medication. So you would probably try and work with that context to determine how many decimal places in order to save the patient's life. So the context always dictates how many decimal places. In maths, with sides, if we're not told, then yes, we often do 2 decimals because the exam is asking us for 2 decimal places. But in life, it's always the context that really does guide us and govern exactly how we are going to do. So today I'm using 2 decimal places. However, I'm not too mad about angles with 2 decimal places, because if you look on your protractors, you'll notice that you cannot measure an angle 2 decimal places. You can maybe measure it to 1 decimal place, but it's very difficult with your protractors to actually measure to 2. So an angle is quite okay to measure to 1 decimal place in our theoretical context, because we're doing theory here. We're not using a practical context. So always, mathematics is a useful tool for practicalities, for contexts that involved calculations, and always be governed by the context to determine the number of decimal places. There's another question that was posted on identities. When working with an identity, what do you work with first? An identity is something that, it's a statement that can be proved true in most cases, and sometimes you're given a mixture of ratios to work with, and the first thing that you try and do is either work with your square ratios to make them one term, and the other thing that you try and do is try and get everything in terms of sine and cos, because out of the 6 ratios, you can write 4 of them in terms of sine and cos. Or actually you can write 6 of them in terms of sine and cos. So that would reduce the amount of algebra that you're doing. And then it's a matter of persevering. It's a lot of algebra when you're dealing with identities. So yeah, you just need to persevere once you've established all your ratios in terms of sine and cos. Right, let's get back to the angles. We're trying to find this angle over here, and we are given this side and this side. And my question is the 13 the adjacent side, or is it something else? Well, the 13 is opposite the right angle, so the 13 is the hypotenuse. So therefore, we could be working with either sine or cos, because they both have an hypotenuse in them. But then I notice that I've got the 7,5, which is directly opposite to the angle. So therefore, it's the opposite and the hypotenuse that I'm working with. The moment you've ticked 2 things, that's the ratio that you're using. So we have sine alpha is equal to opposite over hypotenuse. And so we can go and find the angle. Finding the angle means it's our yellow function, and we want the fraction 7.5 over 13, and we've got a 35,23. Right, and then we've got, I think, 2 more to go. So we've got alpha, and we've got this side, and we've got that side. Question, is this side here adjacent? No, it's opposite the right angle, so it's my hypotenuse. And this side here is the opposite, so again, sine alpha is equal to 1,7 over 2,2. So we get an angle of what? Let's see. Remember, yellow function to find angle It's a fraction, so it's 1 comma 7 over 2.2. And we've got 50 comma 60. So alpha is 50 comma 60 degrees. Remember the unit, it's a degree that you're working with. Okay, let me go on to working with angles but in a different context. Let's look here, solve for the angle. Okay, here we're still solving for the angle. One of the questions that was posted on the Facebook page was around, will we always be given a right angle triangle? Now, the ratio of opposite to hypotenuse and adjacent to hypotenuse and opposite over adjacent will only ever work in a right angle triangle. So yes, to the person who posted the question, you have to work with a right angle triangle. However, trigonometry is not bound just by the right angle triangle. You're going to see next year in grade 11 where you're going to work with angles that are larger, or let's say triangles that are obtuse angled, and you'd like to find some of the sides and angles, and then there'll be other tools that will help you to find that. For now, in grade 10, we do work with the right angle triangle, and I'm going to show you in the next segment how the Cartesian plane assists when angles are larger than 90 degrees. So, yeah, it is a right angle triangle if you're working with SOHCAHTOA. Right, here we've got an equation, cos theta over 3 is equal to 0,102, and we need to find the angle. Now, this is what we'd call a trig equation because we're solving for the angle and we have an equal sign there. Now, whenever solving for the angle, as we saw in these questions over here, was that in solving for the angle, this coefficient over here is 1. There are no terms added, and it's over 1. So coefficient must be 1, denominator must be 1. In other words, this sign ratio must be isolated before we can find the angle. So before we go to our calculator, the sign ratio has to be isolated. So this 3, this fraction, this coefficient of 3, or actually a third, is in the way. We've got to get rid of it. So we need to take it over and say that cos theta is actually equal to 3 times 0,102. Now that we've isolated the ratio, we are able to use the calculator to help us find theta. And so, since it's an angle that we're finding, we need the angle button, which is that button, and we have a 3 times a 0.102. And the calculator will now just give us what that angle is, which is 72,18 degrees, or if we're rounding it off to 1, as we said earlier, which is a lot more convenient, it would be 72,2. But if probably you were using a technical drawing to try and make it absolutely accurate, maybe they'll even ask you to round it off to the 3rd decimal place, because you don't want buildings to collapse. So your decimal places are governed, again, as I said, by the context. So 72,2 will be good enough for our context. So that would be theta equals 72,2. It's an angle that you're finding. Remember the degrees. And as you see, I do not show any symbols, any minus ones. That's how the calculator operates. Your job is to go from the ratio to the angle without showing anything else. Okay, but you need to isolate that ratio first. Right, here we've got root 3 times sine A equals 0,785. And whereas earlier we had a denominator, now we have this ratio over here, or actually this coefficient, which is in the way. So we need to isolate sine A by taking that over and dividing both sides by root 3. So it's 0,785 divided by root 3. And now I know that my calculator is going to give me the angle, so I must just go to my calculator. And we would like the angle using the sine ratio, so it's my yellow button. And we've got a 0.785 that we're dividing by the root of 3. And we want to bracket that. And that gives us an angle A of 26,95. So this 5/500 is going to make that up to the next angle. So let's say 27 degrees. 27,0 degrees. Okay, that just indicates, that comma 0 just indicates it's not 27 on the dot. It's actually, I've rounded off that tenths to the nearest tenth. Okay, then I've got a tan A plus a 5,62 is equal to a 13,256. As we said earlier, I have to isolate this. And I isolate that in the same way as you would isolate an x, as you would isolate an a in any equation. If there are terms, I isolate it by getting rid of the terms and then isolate the coefficients. So here I've got this term that I need to get rid of. So therefore tan A would be equal to 13,256 minus 5,62. So in the end, I'm only looking at tan A. So I've isolated, take the terms across and leave only the trig ratio by itself. If I cannot isolate that tan, I can't use the calculator. The calculator is that last step that you're working to find the angle once the trig ratio is isolated. So we've got this ratio over here. So we can actually say that I want to find the angle. We can do this in one, because we can say that 13,256 minus the 5.62, I can actually do as a unit, and the calculator will give you the angle straight away. So that A is 82,5. Okay? $82,5. Okay, so that was A equals 82,5. Okay, then our last question for the section was, how do you deal with reciprocals? Because there's grade 10s, you working with those reciprocal ratios. So we need to treat them a little bit differently, but the main job is the same with any equation. Isolate that unknown. So we've got sec A is equal to 6,457 divided by 2. Can you see I've now isolated that? Once I've gotten to that step, I'm now ready to say, but if I take the reciprocal of sec, the reciprocal of sec is cos A. So my yellow process is to take the reciprocal. Now, if I do that on the left, I'm going to do that on the right. So my reciprocal is going to be equal to 2 over 6,457. Okay? And once this cos A is now isolated, I can now use the calculator to go and find out what A is. And I think that I've lost the calculator, so we'll take a break.
Let's take a break, okay? So you guys find your calculators so that you guys can help us out. Maybe during the break, you could maybe just finish off the questions and get whatever you need to get straight in your mind, just so that you can ask us questions, because this is actually the perfect time for you to ask any questions that you wish to ask. See you now. welcome back, Mindsetters. As you already know, we are doing trigonometry, and the show has been absolutely amazing because most of you guys have managed to join us on this lovely, lovely spring Monday, and I hope that your weekend as well, Saturday, was Spring Day, the 1st of September. So I hope that you guys had an amazing spring because it's just so warm and lovely in the studio as well. It's nice and warm, so I'd really like you guys to ask us questions right about now because it's so warm. There's no excuse not to. So in case you're not understanding or there was a question in your exam that you didn't understand on trigonometry, please don't fear asking us right now because this is what we are here for. Over to you, Dina.
Thanks very much, Katlego. And yes, grade 10s, we've found the calculator. So let's get back to that question that we were on. We were trying to find the angle A, where cos A equals 2 over 6,457. And I'm sure in the break, some of you would have worked out what that angle is. So let's see what my calculator shows me. 71,956. So I would round off to just 72,0 as an angle. So that would be 72, 72, 72, 72,0 degrees. So that's that angle there. Okay, so let's just fix it up here. There we go. And let's just go down here. There we go. Angle A 72. Remember, angles got little cuppies and the values have got degrees on them. Okay, so that was solving for the angle. Now, what was the question that somebody posted around isolate? They wanted to know, I've used the word isolate. What does that mean? That's just a fancy way of saying, if I've got 4x minus 1 equals 5, I will say to you, solve for x. So solve for x means 4x equals 6 and x equals 6 quarters. Okay. Now I'm using sort of layman's terms and saying isolate the x. So when you are placed in isolation, it's only you and yourself. There's nothing else around you. So currently the x has got a -1 added onto it. Actually, the x has got a 4 that's being multiplied by it. It's got a -1. It equals 5. So when I'm solving for x, I'm actually isolating the x. I'm making it by itself. Now, I'm using the same terminology in trig because when I say solve for x in algebra, it's quite an easy way to say isolate the x. But in trig, it's a lot more complicated to say solve for tan A because you really are solving for the angle, but you're solving for tan A at the same time. And in solving for the angle, there's a couple of processes that must happen. And so one of them is to try and get that ratio by itself. So instead of me saying solve for tan A, which is quite a complex thing, or solve for sine A, or solve for cos A, I'm saying isolate the trig ratio. Make sure that the trig ratio doesn't have coefficients. Make sure that it doesn't have terms attached to it. Then you've isolated. Then you can solve for the angle. I hope that makes sense. So isolating x means x has got a coefficient of 1, it's got a denominator of 1, it's standing by itself. And that's what we're talking about when we're dealing with the trig ratios. Okay, so that was a question on isolation. So let's see what's here. Right, let's see what's there. Okay, so let's go on to 4. There we go. Right, now we're going to change direction slightly. Okay, that's not what I wanted. There we go. That's better. Okay. I'm going to give you a trig equation. And the reason I'm saying we change direction is because I'm actually making this angle an angle that is larger than 90 degrees. And remember earlier somebody asked the question, is a triangle always 90 degrees? For this kind of trig that you're working with SOHCAHTOA, yes. But we can get contexts where angles are larger than 90 degrees. And then what are we going to utilize to help us in formulating the theory that is going to help us to solve for those various ratios? So when that happens, we are going to use the Cartesian plane. And we're going to do two things. Firstly, we're going to have that the way that we measure angles is in anti-clockwise direction. So we're going to have what we call quadrant angles, which is when we rotate to 90. Then if we rotate to 180 and rotate to 270 and rotate to 360, we will rotate in anti-clockwise direction. And then this theta that we are measuring here is said to be in standard position if, I think I'm actually going to find another page here and just do that. Okay, let's do a little bit of theory on the side here and we'll come back to the question. So measure anti-clockwise. And then the second little bit of terminology is that theta will be in standard position from 0 degrees, so it will be rotated in an anti-clockwise direction. And where it stops on the Cartesian plane, it will have coordinates x, y. Okay, now if this arm here had to travel to a new position, what is the path that this theta would, or this ray would follow into the next quadrant? And this blue theta is bigger, so we're going to call him beta. And then we're going to continue rotating into this quadrant. So we've got this angle at this stage, and this angle is larger than 180 degrees. Can you see the path? What is the path that's forming? So it keeps going, path, all the way into this quadrant, and all the way back there. So I think you can clearly see that this angle that it stopped there would be all the way there. Okay, so theta was acute, then it became obtuse, to the pink one, which is reflex, to the green one, which is bigger than 270 degrees. So we are going to utilize this rotation of this ray to help us with the connection between the coordinates of the ray and the size of the angle. And what we call the path that this ray has taken to create all these angles that have become bigger and bigger is obviously the circle. And the circle has got a relationship. A circle is not a function, but it is a relationship that looks like this. The abscissa squared and the ordinate squared will give you the radius squared. Okay? So we've got, at any of these positions, take x squared and y squared and you'll get the length of the radius. Now, what is the length of the radius? Well, it's the length of this segment that's in standard position. So that would be the radius. That would be the radius of the circle. That would be the radius. That would be the radius. They're all radii. Okay? So the relationship between each point and the radius is formulated by that equation. So in each of those quadrants, we're going to find that in the first quadrant, since the angle's acute, theta's acute, and the quadrants work in exactly the same way as you've worked with them in algebra, so it's quadrant 1, 2, 3, 4, we would say that every single ratio that you work out would be positive. However, when you get to the second quadrant, let's look at sine of 120. That's positive. Let's look at the cos of 120. That's negative. Let's look at the tan of 120. That's negative. So obtuse angles have got this interesting relationship. Only the sine of obtuse angles will be positive, but cos and tan will be negative. So we're going to say that in here, we're only going to capture the ratios that are positive. What happens to the pink angles? Well, let's go back to the calculator. What happens to something like sine of, let's make it 210? what do we get? Oh, that's too big, 2,210. Let's just correct that. Sine of 210. That would give me negative. What about cos? Cos of 210. That would be negative. What about tan of 210? That would be positive. Interesting. Tan is positive, but sine and cos is negative. So, tan would be positive in this quadrant. And what happens in the fourth quadrant would be a green angle, so an angle that's larger than 270. So let's take let's say cos of 330 bigger than 270. That's positive. What about sine? 330. That's negative. And what about tan? That's also negative. So as you saw, only the cos is positive, but all the other ratios will be negative. So what we've captured over here is that in each of these quadrants, these are the positive ratios. All the other ones will be negative, the ones that we haven't captured on this diagram. And if you read this word, it says C-A-S-T, cost. So we call this the cost rule because it will be a rule that will govern every single ratio that we'll be working with. So knowing that information, we're now going to take that and we're going to put it onto this information over here. Okay, which was to say that if we are given that information and that information, we must draw a diagram with theta in standard position. Well, we first need to know, is it a theta that's going to be in the first quadrant, second quadrant, third quadrant, fourth quadrant, and this information is going to be able to tell us. So let's work with the information first. If we have 5 tan, let's isolate the tan ratio. So we've got tan theta is equal to negative 2 root 6. So tan theta is therefore negative 2 root 6 over 5. Can you see that I've now got a negative ratio? And our cost rule, which we're just going to put over here, says that it's only in quadrant 3 that we've got a positive tan ratio. But in those two quadrants, 2 and 4, tan is negative. So I'm just going to capture the information in the two quadrants with a little tick. So we could have tan in there or we could have tan in there. And the next little bit of information is that the angle must also be between 0 and 270. So this quadrant here, quadrant 2, shows us that both of these restrictions, the tan is negative and the restriction on the angle, will actually happen in quadrant 2. So to draw the diagram that they require would mean us taking a quadrant, drawing in the angle, so it's rotating from 0 degrees all the way to quadrant 2. We would then fill in the radius and say that this is the angle we're referring to. But the one thing that we haven't discussed is how does this ratio impact on this picture since it's not 90 degrees? Okay, well, for that, we actually have to go back to the theory board. So let's go back here and just give you a little bit more of definitions. And that would be that for any angle that's larger in the Cartesian plane, we define the ratios in a slightly different way. So we've got coordinates as opposed to opposites and adjacents. So we'd have y over x. So these are the definitions for each of those three ratios. I'm only going to go over those three. The reciprocals will work in exactly the same way. And for this acronym, we often say, well, some people have used, not we often say, but it's good to just put the capital letter C, X, R, and T, Y, X. And something quite funny is to say, how do I remember this if it's for the Cartesian plane? And that is shield your rear, cause X rays tan your exterior. So that will be quite funny to remember that. But this is the Cartesian plane's version as opposed to the version that we started the lesson with, which would only apply to right angle triangles. Okay, so let's go back to the diagram that we were busy with. And we've now got that the definition of tan on the Cartesian plane, shield your rear cos x raised tan your exterior, is y over x, right? So in this quadrant, it would mean that the y value, it is positive, and the x value is negative. So my negative would have to accompany the denominator, and that will be negative 2 root 6. Again, the context governs us. Any x's are negative, and the y's are positive. Okay. Now, if I say a negative divided by a positive, I'm still getting a negative ratio, or a negative divided by a positive, I'm still getting a negative ratio. So when you convert back into the Cartesian plane, be very careful about the signs that you are using. So standard position then means that we have the radius and an x value and a y value, and we've got the size of the angle. So standard position is really in which quadrant will that angle lie in. Okay, now to end off, we will look at, with the aid of the diagram that we've just drawn and without using the calculator, okay, evaluate what 14 cos theta plus 7 root 6 sine theta would look like. Well, 14, the definition of cos theta would be x over r plus 7 root 6, and that would be y over r. So we could now substitute in, and we'd get 14. The x value you saw was minus 5. We then have to work out what our r is. 7 root 6. Y was, let's just go here. We haven't yet worked out what our r is. So we would get x squared plus y squared would be equal to r squared. So x would be 5, and y is 2 root 6 squared is equal to r squared. So we would get 25 plus 4 times 6, which would be equal to r squared. So it's 24 and 25, which is 49. So therefore r would be 7 in this context. So we get a 7, and then it's 2 root 6. So let's go on to our next page. And this r is 7, we've worked it out now, and this y was 2 root 6 over 7. Okay.
Dina,
So, yes.
our time is running
Oh,
out,
okay.
but you can carry on with
Okay,
that
I'll
just to
finish
finish it
that.
off.
So that's negative 10, and that's 7, 7, so that would be 2 times 6 is 12, plus 12, so we get 2. So that's just working with angles that are bigger than 90. We'll do a lot more of that in grade 11 as well. Thank you.
Thank you, Dina. Guys, as we know, it always goes so super fast when we're having fun here at Mindset. I think that they should start making the hours like 2 hours or 3 hours, just so that we have enough time to cover everything. Thank you guys for such an awesome show. You guys were absolutely amazing. Remember to keep learning extra and learning more. Thank you again to Liberty. It has been an absolutely fantastic, spectacular show. See us next for grade 11s if you want to join us. Bye, guys.